Embedded Harmony, orchestrating general purpose computing, hardware acceleration, and standard software. I'm really happy to welcome the panel moderator, Darren Buttle, Head of RTA Solutions from ETAS. Darren, welcome. This is your applause.
Thank you very much.
Enjoy.
Thank you. Go.
Yeah. Okay, so thank you very much, everybody, and welcome to the next panel session where we're talking about embedded harmony, orchestrating general purpose computing, hardware acceleration, and standardized software. So on the panel today, we have Thomas Röhrke from Infineon. He's a hardware software architect, and he's also responsible for Infineon's engagement in the RISC-V consortium, so driving modern instruction set architectures. Next to Thomas, I've got Mars Huang. He's a project manager, and he looks after the switch and transceiver ecosystem for Realtek. So again, a company that some of you are old enough to remember from graphics cards in the 1990s. But actually, this is a kind of thing that we're now seeing in automotive. And last but not least, we've got Jonathan Siegel. He's the software product manager at NXP. And thank you, panel, for attending today.
Thank you.
Thanks. Okay, so you might be wondering why in a conference where we've talked a huge amount about software and software-defined vehicle, why have I got three hardware dudes sat on the stage with me? And actually, there's a reason for this, that if you're looking at a lot of the things to do in automotive, in automotive development, we talk a lot about software, but actually, a lot of the innovations that we're delivering in software fundamentally rely on the capabilities of the underlying hardware. They rely on what we can do in terms of sensor technology. They rely on what we can do in terms of control technology and actuator technology. And increasingly, they rely on the amount of technology we can have for moving data backwards and forwards within the vehicle. So one of the things that I want to sort of start talking about today is the importance of the hardware platform and the importance of the low-level software that talks to that hardware platform in order for actually people to deliver all these software-defined vehicle innovations. So we're sort of right down at the platform level. We're down at the level of putting the foundation into the building to allow everybody else to build everything on top. It needs to be safe, it needs to be secure, it needs to be high performance, it needs to be low footprint, and it needs to really dovetail together the embedded software, which would be the ETAS part of the jigsaw, with a load of the embedded hardware and the associated drivers. So the first thing I'd like to ask is, from your individual perspectives, what do you see are the key trends that are happening in the silicon industry as silicon vendors? What are you seeing in terms of the adoption of large-scale devices, small-scale devices? What's happening in the zone controllers? And what's your opinion on the split between use of dedicated ICs for things like motor control, things like switches from and more general purpose computing? So I'll start with you, Thomas, because you're the closest to me.
So what we essentially see as a trend is basically the transition of the EE architecture and how this essentially changes the requirements breakdown coming from the EE architecture to the microcontrollers which we develop. So in a sense, what is basically a desire. So we are not basically in the central car computer. We might be in the zones. A high desire of compatibility is essentially required to make software easy migratable, easy enablement there. While on the other hand side, one would still like to leverage, let's say, the advantages of having a very specific hardware, which is, for example, it is power friendliness, efficiency, real-time currency characteristics, all that kind of stuff. So this is something which is driving us and has started to drive us already the last years. And I would say this is basically currently in a transition phase, because if we are looking on the different EE architectures, there exist various different models still. And I think we are still some steps away from a consolidation to the one or even three single models, let's say.
Yeah.
Okay, so I'll hand over to you then, Mars.
I think the dedicated IC, you mean that means like our switch. And I think the larger SoC should be more care about the more general purpose, like something like that. So it will be like mainly many manager to make a decision to do the many to collect a lot of information and then make a decision. But the dedicated IC should, like the switch, need to focus on the dedicated functions. They need to transfer the impact packets and to the manager to let them do the right decision. So they will be, but our switch might be more need to let them be more smart, I think. And in the future, if we define the more smart, that means they need more software, I think. So the software, more software, more application, they will let our switch more be like the can be compatible in the SDV world, I think. Yeah.
Thank you. And Jonathan, I'll hand over to you as the...
So can you hear me? Yeah. We see every type of architecture. Yes, there's a part of consolidation, as Thomas said, but what is consolidation? Sometimes you have smart sensors in the edge or smart mechatronics, meaning smart, either they are very focused on doing something or maybe they're powerful, or zonal aggregators that just passes information to a central zone, or zonal who are more intelligent and have some kind of functionality. There's no real trend in saying this is the way it goes, this is the way it goes. It depends very much. If you're in China, the Chinese have a very specific, and not all Chinese, I mean, particularly class of customer have a particular idea. If you look particularly in the West Coast of USA, people coming from the IT, not from the automotive, they want to have a server-like kind of architecture. So you see a lot of centralization and consolidation. For the traditional car maker, I would say they're still in the PowerPoint mode. They're in the experimentation world, but they want to go there, but they're not there where they say, okay, we just don't need to consolidate. We need to start splitting features so that, things are done at the edge in one way and the function are going to be put somewhere in the centralized. So let me put it this way. The biggest trend is probably to have a more intelligent central compute, and it depends what we define central compute is one big or a lot of small together, and the zonals. The zonals is probably the key element in the next future architecture.
Yeah, I mean, this is something that we've also observed that that begin to be lots of aggregated systems from a purely federated system. A lot of the things on the OEM side moving into that central compute function, bigger SoCs, and lots of what I would describe as decision logic problems. Yep. Does the car stop? Does the car go? Do we move left? Do we move right? But actually, one of the reasons that we've heard a lot about in terms of the OEM management of the tier 1 platform is that if you've got a number of ECUs that are trying to control where the car is going, actually you're paying, as an OEM, you're paying the tier 1 to develop that functionality multiple times, because each, Park Pilot, ESP, ABS, automated driving ECU, they're all probably deciding some kind of stopping or going function. But actually, it's really difficult at vehicle integration time to bring all of those two things together and make the same decision in 7 or 8 different ECUs, essentially looking at that. So that splitting of that sensing and technology function away from the decision function actually involves a fairly fundamental change in how those ECUs are federated and aggregated in the future. I'd also kind of like to touch on, as we're moving to bigger zonal controllers, those chips are really complicated. So, and I'll start with you, Jonathan, this time. How do we get that right? So if we're looking at a chip where we've got a whole bunch of, say, ARM A cores and R cores and M cores on that, we've got some RISC cores and coprocessors, it's not uncommon these days to see bigger devices with essentially 30 different bits of compute platform on of that. And one of the challenges that we see as a software provider here is actually getting the chip to boot predictably. How do you think we get this right in the future? Because we're moving a lot of that software startup and mode management issue into the hardware.
So what is the question exactly?
So how do you think we try and get these ECUs right? What would be the approach of NXP, for example, in terms of making sure that when we've got this big aggregation of different CPU cores into a piece of silicon, that actually still becomes predictable and maintainable and secure. And
So let's see it historically. At a certain point, the silicon vendors were actually working in order to satisfy a Lastenheft, so specification from the tier one. This is changing in the sense that we silicon vendors are coming up with our own silicons based on market observation, and we gave it to the customer. So until a couple of years ago, we threw it over the fence, and then the customer came back to us and said, hey, do you have also software for that? Oh, no, we don't do it. Go down to the alley. The guys from ATAS do it. And they came to you and said, oh, yeah, do you have something? Yes, but it's not really silicon specific because it's an OS for everything. And this didn't really, customer didn't rejoice for this. Now, we're not stupid. I mean, not me, my colleagues, not stupid. So we understand that we have to step up, and we are working more and more together with you and others in order to make sure that the specific IPs of the hardware needs to be done by us and integrated by you.
Yeah.
So it's a complex thing, and the bigger these things become, the more third-party, open source, AUTOSAR classic things come on one platform, and there needs to be a kind of pre-integration, and this is where NXP is going. Maybe somebody heard about this Core Ride.
You've got the Core Ride initiative,
where we need to step up and say to the customers, we are taking care of this. If the world of the classical tier one is not there anymore, somebody needs to do it, and we will do it for you.
I think we'll park that a little bit there, because that's a topic I want to come back to in terms of how we actually manage the hardware software interfacing boundary. One of the things I'd like to just loop back to in terms of hardware architecture design as well is we've got essentially one of the things that we see as a software supplier is, I would say, it's the death of the proprietary architecture, or that's beginning to what it looks like. So if we go back 20 years, every silicon vendor, its own proprietary architecture, and then consequently we would then do ports for each different device. One of the things we've seen a lot, and we see this accelerating, is a big move to standardized instruction set architectures. So there's a huge amount of ARM devices out there, or ARM-based devices out there, and we're now beginning to see the adoption of things like RISC-V in certain categories of devices. So what I would like to get your feeling with, and I'll start with Mars actually to start with, is how do you make your design decisions about what your CPU core architecture is, and how much is that an important design decision in comparison to your peripheral space and your hardware acceleration that you're building?
Yeah. So I think we first of all we need to know the software requirement, and this software requirement must be coming from the software vendor in the future, I guess. So in our point of view, if we don't get such software requirement, they will be very hard to get such a new idea or new software requirements. So in the future, we put a lot of resources to collaborate with the software vendor, and the software vendor, we hope that they can help us to analyze such a requirement or new idea to us, and we can discuss together to find a better solution or better new hardware chips that is possible. And our target is to build a general a platform that can work together with the software vendor and the software open source, something like that, and we can have a better collaboration with together.
So you're looking at actually trying to essentially make the best choice for the chip based on the instruction set architecture and CPU core, but then try and hide as much of that as possible in the software stack, so it's transparent to a particular user of your categories of devices.
Yeah.
So let me come to you, Thomas, now, because what are your feelings here? I mean, obviously, with Infineon's portfolio, we've got a lot of ARM-based things with the Travio. We've got a lot of proprietary architecture with the well-known and well-respected Tricore architecture. What are your thoughts here?
I think, first of all, you're absolutely right. When I'm talking about large zone controllers, I have to master real high complexity. Yeah, you have more cores, you have more power domains, you have more fine granular switching, more transitions, all that kind of stuff. and here you have to cope essentially, I think, from two things with the complexity. The one thing is that, like Jonathan said before, it's not sufficient anymore to say, okay, I'm having basically an RFQ, and this RFQ is relatively detailed, saying what I have to implement, right? But you might need, let's say, to observe the market, consolidate different RFQs, right? And try to build essentially a vision of what the thing should do. So we are coming into a more and more proactive role, right? And this is basically, let's say, to give it a name or a term, this is maybe use case driven development or use case driven architecturing, however you phrase it. Okay, so this is the one thing. The other thing is basically when you would like to not only cope with high complexity, but also have short turnaround times, what you basically need is kind of, let's say, platform-based thinking in development, right? Which in the end says you need generic approaches which can scale over a relatively wide range, because it depends on how you define the zone controller, how you define the in-vehicle network and architecture, right? The requirements to the micro are vastly different. So obviously you need something which scales. A pretty much nice example, you have already mentioned it, from a core architecture perspective is RISC-V, right? And this has advantages both for our internal development, because all your, let's say, development activities are focusing around, let's say, a unique architecture which is well understood and which can be nicely scaled. And this helps internal development on the one hand side. Yeah. On the other hand side, it definitely also helps our customers. It helps software providers, something like this, because they are essentially coping with the same hurdle, right? They always need to, with getting a new architecture, they need to get, let's say, over the Helios point, right? And then proceed from there, right? And the better you have something which is on the one hand standardized and on the other hand scaling, the better you can also do in your SoC development in the end vertical integration. And the better you can do vertical integration, obviously the lower, let's say, the tendency is to have silicon bugs even in complex products, right?
Yeah.
So Jonathan, coming to you, I mean, I'd like your sort of input in this, because I know in terms of particularly the CoreRide architectural family that you've got, where you're scaling from extremely tiny single core devices up to enormous multi-core devices, and you're actually just using essentially ARM-based silicon across that platform. But I know you're also doing things like putting RISC-V into things like the hardware accelerators. How do you make those choices in your organization, and how do you think that influences customers' buying decisions? And I'd like you to then look at that also from, do you think customers care about the core, or is it actually the peripheral set on the chip that's important?
Okay, let's start with the first question. So we're a bloody automotive company.
Yeah.
So we actually do what we see customers wanting.
Yeah.
And customers in the automotive are,
Special.
well, diplomatically say, conservative. So if there is a kind of inertia coming from, ARM, and ARM, everybody feels kind of comfortable with ARM. So for the cores, they know what an A core is and an R core, even if there are multiple flavors, but this is it. So if we would come up and say, our next generation is completely everything on RISC-V, we will see a couple of sweating drops on the front of our customers. I mean, good luck. I think it's going to be fun in explaining them. What we do is we provide, nevertheless, because we see also this push, RISC-V seems great. You know what? We're going to put a couple of these RISC-V. We're going to give them a good opportunity to be proven on specific use cases, and then let's see where we pick it up from there. If we need to change from there, to a RISC-V based core, great. I mean, I hope nobody from ARM is here. They have
There are. I'm looking at one now.
Is the one. ARM is not what you call cheap, not at all. So it would be actually also good for us not to use it. But at the moment, it's the most stable one. So basically, if this is the answer to your question, is it's basically based on what our customer expects. At the moment, let me put it in this way: at the moment, automotive customers see so much changes, real changes, bullshit changes, whatever changes. They don't need a systematic or a big change in architecture from the cores, not from us.
I mean, I know from speaking to some silicon vendors, it's almost beginning to be a checkbox item that does it have ARM in it or does it have RISC-V in it? And if you can't answer either one of those questions, people are now beginning to be more reluctant to pick the device up, even though if you look at historically the proprietary architectures, they are really absolutely fabulous at the job they do. And I know we get occasionally concerned about this, that if you're just talking about data processing and essentially brute force, then either one of those architectures works really well. If you're talking about really low latency, tight real-time control, it becomes much more difficult. So how are you going to actually look at the tight real-time control? You can sort of getting Tricore-like performance with a sort of RISC-V based ISA, because I'm guessing it's all down to interrupt control management.
Yeah, it is. I mean, obviously, Tricore is a class of its own when it comes to hard real-time requirements, right? And it still holds true. Yeah. The question is obviously when you have this change in the architectures, to how much extent you still see this. Real tight time boundaries, right, for which Tricore was made of. This is the one thing. The other thing is that most of the stuff which is, let's say, bringing the benefit here are micro-architectural means, right? So it is essentially still about getting a tailored micro-architecture for a specific job, right? Nevertheless, having as far as possible standardized interface for the software.
Yeah. I know one of the things that we know from particularly doing things like operating system porting and things like this, that if we go back a number of years where if you go back to the early ARM7 days, for example, lots of ARM7 based silicon and everybody built their own interrupt controller and they were all different. And you just had the FIQ and the IRQ and a big multiplexer on the front of it. Actually making that work reliably across every single silicon vendor's different flavor of that, it was quite a significant part. In fact, it was most of the effort of actually doing our job. As we found with particularly on the ARM architecture, where you've got the sort of GIC and the GVEC, standardized interrupt controller peripherals and block sets for that, that's made it much easier. We can spin up ports on ARM much faster than in the past, because a lot of the actual work of making our software, and particularly our OS work on that, is now semi-standardized. Yes, the peripherals might be mapped to different register locations, but actually it makes it much easier for doing that interrupt controller control. I'd just like to briefly touch on, we talked a little bit this morning about open source software. Actually, we touched a little bit here on open source hardware. Do we think the automotive industry is ready for open source in the hardware? So i.e. taking an open source instruction set architecture and leveraging that. I mean, there's a little bit of a reluctance to having open source software already.
Okay.
Who wants that one? Go on, Thomas, you can take that.
So I think we have to distinguish two things. With RISC-V, it's open associated. It's an open ISA, right? And this is basically the ISA aspect. But what you're doing then in terms of implementation, you can either do as really open source hardware, like we know from the Open Hardware Group or something like this, or you are getting a commercial product. As Jonathan said, automotive is tending to be conservative. You correctly said, right? But apart from being conservative, it definitely has also something to do, let's say, with liability, predictability, and all that kind of stuff. Yeah. And from this perspective, just taking open source hardware from the shelf, I consider is rather challenging.
Yeah. I think somebody mentioned it when we talk about the open source software. It's not the fact it's open source, it's the fact that do you trust the person who's integrating that to do the job properly? And obviously, if you're a mainstream silicon vendor doing that, it becomes much easier to trust you because of the pedigree of the organization.
Maybe just only one comment, because we talked about open source and everybody's excited a bit. Are we ready for open source? You asked hardware in the microcontroller.
Yeah,
I agree. Challenging, I would say probably not. But we're not even ready as an industry to embrace open source in the real-time domain.
Absolutely.
Okay, so we talked here about how good it is, open source, but we're talking about powerful HPCs. Okay, so maybe as a comment, how conservative we are.
That's absolutely true, because actually as soon as you get down to the hard real time, ultra safe, ultra secure area,
It's AutoSAR Classic,
it's AutoSAR Classic there.
for your joy.
Which is great. So that gives me a nice lead into talking a little bit more about software then. So if we look over the last 20 years, and AutoSAR Classic's a really good leading for this, that we've done a lot of standardization in the software. And I mean, everybody here is probably familiar with AutoSAR. It has some good points, it has some bad points. It's very, very complicated, lots of pieces in there. But actually, some of us are old enough to remember how bad the world was before we had AutoSAR, and it was much worse than it is now. But given all that software standardization, that sort of driver architecture standardization and basic software standardization, actually, if I look at all three of you, you compete in the marketplace by putting proprietary things into chips and making that the value add that you're wanting to sell. So how does that marry together with having standard software? So how do you go from a standardized software stack? Because at some point, in order to leverage your hardware capabilities, it's got to be going into the proprietary world, and we've got to somehow make those two things work together. I'll start with you, Mars, actually, because you've got a really specific, okay, you're building switches, transceivers, very, very specialized hardware domain, lots of expertise, very few people who do that. Now you're putting AutoSAR onto that in automotive. What does that mean for you?
Yeah, I think generally it still need to depend on the customer requirements. For example, the AutoSAR stack is a really huge lot of modules. If we put it all AutoSAR modules inside the switch, it will be difficult to calculate the size. And because of the hardware resource of the switch is limited, we are not like the SoC or NCU. They have a much more
about 20
resource.
megabytes of flash.
Yeah, we only maybe have a 1 megabyte. So we must to think about what kind of the application they want to. So for example, and also because of hardware features, they can help the software to do better for the protocol, I think. So for example, if we can use the hardware to offload much offer like the protocol things, and they will be better if we can do that, because hardware always faster than the software, I think. But it will be depends on the cost, and also depends on the customer's application. So yeah, we trying to do that, do our best. And questions, sorry.
No. I was just about to say, yeah. That I think that's right. I think there's a essentially cherry picking enough of the stack to run on that device, and then actually exploit and leverage the hardware capabilities essentially through a set of drivers that somehow interface nicely and tidily to that. What's your approach, Thomas, for the Infineon side?
So I think there are still on SoC architecture some distinction factors, where you can do things right or wrong depending on the application which you are trying to address. For us, still very important is the aspect of safety, security, dependability, that kind of things, and that actually also that we were quite leading the market over the last years. And the thing is that there are sufficient other fields where you can still distinguish, for example, application-specific acceleration, which you can more or less well integrate, right? On the other hand, we still have to say that when you are implementing a very specific solution, right, you still have to find this trade-off between, okay, I have something which is nicely portable and I'm not leveraging specific features, right, to the point that I am saying, okay, I have a fine-tailored solution which might be more efficient. So in this sense, it is also here has to be found a trade-off between essentially, let's say, the cost of leveraging a new specific solution, versus what you can essentially gain via this, and there will still be, let's say, sufficient room for differentiation.
So
I would be a little bit more controversial on this. I don't think that, at least for us, NXP, standardization is the solution here. I mean, at the end, particularly in the real-time domain, if customer comes to us and they have a trade-off between performance and let's say, portability, they will take performance. So we as NXP, a couple of years ago, already decided we need to step up and provide the functionality, the enablement, the software enablement, in order for our customer to exploit the accelerator that we think are, differentiating from the competitor. So the solution is not asking people like you to make it compatible to us. The solution is to come to you and say, you have to integrate our stuff so that our common customers will take the benefit of portability up to a level, the basic, but then be able to exploit our particular accelerators.
I mean, that begins to touch on things like tooling ecosystem, actually, because I mean, we've talked a little bit about open source, and everyone thinks, oh, it's open source, it's running in the ECU. Actually, I think in the real-time, deeply embedded domain, I think the more important player for open source is actually the tools integration aspect of this. So that when you come with your special bit of hardware magic and your special bit of software magic to drive that, there's a much simpler and easier way of integrating that in the tooling ecosystem than having to do tool breaks in workflow. Yeah.
Although standardization and open source in this case are different.
Yes,
so
absolutely. Yeah.
if I were responsible, I would have actually zero problem in taking the software that runs our special IP and open source it. BSD, get it out.
Yeah.
But the problem is, are you going to take it in your product because it's so special to us that you're going to make it standard? I don't think so.
Yeah, and we probably can't maintain it because you're the hardware guys and you know how it works. Yeah,
exactly.
Yes, yeah. So I mean, in terms of, I mean, we've talked a little bit about sort of what's in the hardware. How can we help on the software side of things make it easier? I think you've basically touched on this. It's essentially about how to make your drivers, your accelerators more easily dovetail into what actually we're providing in terms of the more standardized, target neutral parts of the software solution. Yeah,
I think this is absolutely key. So all the specific accelerators will not help you so much if they are not, let's say, conveniently nicely to program. Yeah? And this is a little bit the question on which level you would actually like to start. Yeah, but in general, I think the expectation from the market will be that you don't have to go over this high apex, which I have described before, but that you have an easy entry, irrespective of whether the solution is standardized or not. Yeah, but you need let's say a decent stack above, and this in the end does not stop at middleware OS, but particularly code generation flows and all that kind of stuff is really required to leverage it.
Yeah, I mean. The sort of, particularly in the networking stack in Autosar, where you've got a huge amount of complexity already. There's a massive amount of complexity in the Ethernet stack. Actually, if you want a normal workflow, you get an ECU extract from your customer, you've got a piece of hardware from you guys, you buy some software from us, and you just want that to work with the maximum amount of hardware acceleration. And so actually, if you've got a workflow that involves pulling a frame up the stack into COM and pushing it back down the stack, but actually there is hardware acceleration for frame relay on the chip, what you actually want to do is just use it, and you want your transparent workflow from dealing with that with the OEM's networking to just seamlessly flow into oh yes, this hardware acceleration on the chip, checkbox, make it so. That's I think how most users actually want to be able to work. And then I think there's then the handover between how does that workflow look in terms of offboarding processing, and then custom code generating that. And I think there's an interesting tooling issue there that needs to be looked at. Okay, so at this point, I would like to stop asking questions myself and ask if there are any questions from the audience or from anybody online.
Yes. You're very clear.
All very clear?
Oh, yeah.
Okay, in which case, I will ask another question. We touched a little bit on this when we talked about switches, and you said you've got a megabyte of flash on your switch. Now, I'm an old dude, so I remember when a megabyte of flash was more space than I could possibly ever imagine using. We were building ECUs that had 64K of flash in there and 4K of RAM, and they weren't doing radically different things to what they're doing today. And if I start looking at a lot of the interesting smaller nodes, if I look at your S32K parts, which are kind of quite resource constrained, actually where we're finding those devices getting used, that's That's small stack devices. That's things where you've got 256K of flash and actually you just want to run a full stack in that. I personally don't see a problem with that. That's a fairly easy thing to do. You can get a stack into 50, 60K if you're careful. But actually, a lot of people aren't careful. A lot of people, it's very easy to bloat up the application, the basic software configuration, the applications achieve much more than we were doing in 64K or 32K 10 years ago or 20 years ago now. Is this something that you also see, that as you add more space to devices, people just put more software bloat in there rather than actually optimizing the software?
Yeah, what's that?
You're laughing, so you can answer.
You have to be careful.
Yeah.
This is what you said.
Yes,
right?
yeah.
And depending on how careful you need to be, it costs more or less money, right? This is the one thing. The other thing is basically that obviously in order to be careful, you have to have deep expertise, right? Mm-hmm. Which makes you finally careful.
Yeah.
Yeah, I think because switch will be in a different type, and maybe if we put the switch at the edge side, that means that they will be more simple. They only need to focus on to forward a packet or something more simpler tasker. Or like if we put a switch at the maybe HPC or centralized sites, they need to more resource to do that. And currently we are expected software vendor to input some interesting switch application or something new idea for the switch. Then we can evaluate what the resource we should put it. Yeah. But currently switch maybe only focus on the firewall or PTP or something like the general features for now, but in the future we expect it.
So picking up that topic of dedicated so in the Realtek case, you've got a dedicated IC for a dedicated job. If I then move to something like the S32 Core parts and the much bigger parts, sort of the N's and the Z's and that kind of thing, do you think there's actually a design paradigm that we can learn from looking at dedicated ICs, where what we're actually going to do is we're going to zone a much bigger chip and actually put simpler software into each zone? So like use a hypervisor, create a partition, drop a simpler software stack that's easier to integrate, easier to maintain, easy to over-the-air update. Is that a design pattern that actually makes it simpler?
It depends. So actually, everybody wants to, we want to have portability. Oh, great. We want to have abstraction, software and hardware abstraction. But when the shit hits the fan, oh no, we're not going to do this. It's too complicated. So we have a plethora of architectures. And I mean, CoreRide, what you address, and I don't know if everybody is aware of what it's doing. It's not just an integration on one particular chip, but it's actually an integration of the software. Let me say pre-integration on the software, use case driven on several SoC and all the SoC that are needed in order to help a particular use case. Now, what do we need there? It depends from what the customer wants. If the customer are more risk aware or risk friendly, which is in the automotive still not the case everywhere, they will go for cut everything, put all the functionalities and the logic in the central computer and the zonal aggregator, have very, I call it dumb sensors, but actually very smart, very specific ones at the edge. And we will have an enormous portability across everything. Now, if you are a bigger OEM with, a lot of platforms and a lot of car makers,
a lot of volume and small margins,
and a lot of risk, failure that you could have, then you probably will not go in this way. You're probably going to take whatever you had before and try to bring it as is in the newer architecture. So there will be not a big shuffle of architecture in the sense of, when we talk about what is EE architecture, yes, it is consolidation, but the reality, the big difficult part is the horizontal cut of things that are sensed and done and things that are thought and processed.
Decide. Yeah,
exactly.
Absolutely. And I think, we touched a little bit, Thomas mentioned this in terms of zone architectures. So what is a zone? That's a sort of quite a fluffy thing, and you see either geographical zones or application zones and things. And I mean, 5 or 6 years ago, we were all talking about zone architectures, and everyone's got some kind of zone controller sort of ECU platform. Actually, there's not been that much of adoption of that. And I think the reason for that is exactly what you described. It's that actually making those software architecture decisions to be able to exploit that EE architecture, that's actually quite a difficult job to do. Yeah.
But admittedly, the pressure is there. The pressure coming particularly from Asia, from China, it's extremely high. The OEM, the traditional one, have the feel that they have to do something. Sometimes they are a little bit entropic in the things that they do, but they see that they have to add speed. They have to add something, not only the process, but also the product that allows them to scale at a very quick, time. If I can quote, I had a customer a couple of days ago that he spoke. He said, our expectation is to from change to deployment in the car within 1 hour. I know that you come from the AutoStar Classic world. It's not a concept that you understand, but but this is actually the expectations that they have.
Yeah.
And this puts a lot of pressure on all the others to change the architecture to make it happen.
Yeah, and I mean that's essentially that design for software maintainability as well, and to provide incremental reuse and incremental build. Yeah. Okay, so I think if there's got about 5 minutes left, if anybody wants to ask any more questions, do we have anything from online?
Online, no.
No, excellent.
Here we have one question.
Oh, wow.
The microphone. Oh.
You weren't so clear then. Look, question.
I have a question. MIPS and ARM. We discussed MIPS and ARM a few minutes ago, and Thomas is more on the ARM side, on the MIPS side, more on the ARM side. And what about China? So China is a growing market. You talked about the conservative customers here, OEMs in Central Europe. How about the OEMs in China? So are they moving to MIPS or to something else, or are they staying with ARM? What is your observation?
I have opinion here. Do you want to go? Or
I have also a strong opinion, so I give it back to you.
Yes. So I think we see particularly in China high interest in RISC-V due to openness in the architecture. So you see there really lots of people contributing. We very interested. IP suppliers coming up, something like this. ARM is still a standing term, I think, in the market. Yeah, and will be for a while. Yeah. So time will tell us how this will end.
Yeah, I mean, I would say from our side, so we do a huge amount of work with Chinese silicon vendors, and to the extent that every couple of weeks somebody appears, knocks on the door, and asks us if our stack supports a device from a vendor we've never heard of before. To a first approximation, it's all ARM based. And when I started picking away at why aren't you going down the RISC-V route, the actual reason now is it needs to be fast. As a silicon company, we didn't exist 18 months ago. Now we're in fab. And the only solution they have at the moment to be able to do that is to actually license the ARM IP to do it. And so they're not necessarily looking at the flexibility and what the MIPS architecture can bring in the future. It's what can they do now so that they can deliver in incredibly short timescales, and that's sort of driving it. I think as the RISC-V ecosystem gets more pedigree and more adoption, and actually with Infinity doing a really good job of pushing that forwards, but also as there's a much more of an ecosystem for peripherals and interrupt controllers, so there's more of a sort of, the Germans would say, a Baukasten system for that. I think that will also help the RISC-V adoption in the same way that if you look at ARM and ARM's plethora of peripherals in and around the ARM Cortex architecture, that actually is the deciding factor. It's the ecosystem around the CPU core rather than the core itself.
I think, to be fair here, the question has to be answered, or it is a question to the question whether it addresses, let's say, current state or short term, or what we see midterm, essentially, right? So in this sense,
we have also to see that, and this comes into the picture, Chinese are extremely pragmatic. So a couple of years ago, we thought, these guys are going to come and disrupt everything that we have here and throw out everything. No, the first thing that they said is we're going to pick AutoSAR. Such an old technology, yes, because it's the quickest that brings us to safety.
Yeah.
What about ARM? We're going to take that. We don't have time, to explore stuff. First thing in 18 months, a car on the road, and then let's think about later something else. So I completely see the
There's a
same
very,
thing.
very interesting quote from Freeman Dyson about this, about sort of how do we engineering. It says that, so he says, good scientists invent new things, good engineers build new things with as many old things as possible. And it's essentially
It is exactly what is happening.
When the technology is tried and trusted, it's much easier to build something on top of it. And if I come back to where we started, where I talked about we're building platform, the important thing about the foundation of anything you build in the rest of your vehicle is that stuff actually works. And the easiest way of doing that is taking things that we already know work.
Yeah.
And then you can build the elaborate things on top of it.
Yeah. By the way, but even our Switch, we consider the RISC-V, and we have such product this year. Yeah. So RISC-V is a new opportunity even for our preferred chips vendor. Yeah.
Mhm.
I can say because you've got actually devices that different price points with actually different ISO architectures in it. Yeah. Okay, so on that point, I think it's a good time to finish. Thank you very much for your attention, everybody, and enjoy the rest of ETAS Connections.
Thank you. Thank you so much, gentlemen.